Okay, thank you. So I'm going to talk about a method for mining conceptual representations from data that we have developed here at SICS. And really unsupervised learning of abstractions from data is really one key component for human-like machine intelligence. And it's it's not very practical to always reason about data in terms of its basic constituents, and it's even in many cases it's completely infeasible. So we need to be able to extract conceptual representations in a data-driven manner, and this is not only necessary for learning machines, but also in analytics for humans, to aid humans to make sense of data. So as humans, we are very, in our everyday lives, we are very good at conceptualizing data. But if we face big data, we really it's necessary to be able to do this automatically through machine learning. So let's say that we observe some type of objects. So this could be words in a text, in the corpus. It could be people. It could be proteins, or it could be, more generally, it could be states in a dynamical system. And we want to describe these basic constituents in terms of on a more general level, in a sensible way. And we want to find different levels of abstraction, not only one, depending on the application at hand and which levels which details are really relevant. So the challenge then is to, given the original observations, to find these other levels. So again, we have our objects that we can observe from data, and we have correlations between these objects. So this can be, if we have people, it can be the connections in the social network. If it's words, it can be their co-occurrence patterns. Proteins, it can be their interactions, and so on. So, given this information, how do we relate the objects in terms of similarity? And what do we mean by similarity? Is there a general notion of similarity that we can use? And here, as a starting point, we use this the distributional hypothesis that is commonly applied in computational linguistics. That a word is characterized by its how it is distributed in text or in spoken language. And this is summarized by this famous quote that you shall know a word by the company it keeps. So what we do here is that we generalize this notion. We say that, okay, you shall learn an object by the company it keeps. An object can be all these things that I listed previously. So what do we mean by company here? So let's say we have our objects here again. Then the company of an object are the neighbors of that object, the other objects that it is correlated with. Now this is the context of this object, its neighborhood. And then we make this assumption that if two objects that are similar, they also occur in a similar context, that they are correlated similarly to two other objects. And in a way, they are therefore exchangeable. They play similar similar role in the data in terms of correlations. And this we quantify this. There are several possible ways to quantify this. Here we use a similarity measure based on the relative L1 norm of the difference between the correlations for two objects. And okay, so of course we want to. The goal here is to be able to do this for really a huge number of objects and a huge number of correlations. And to enable this, we can use these two properties of this correlation graph. So the first one is that two objects that are similar to some degree are at most one neighbor apart. So they share at least a neighbor. Also, I will come to that later. So since they are, we have this locality, it's sufficient to look in the nearest neighborhood of an object to find similar other objects. So in practice, we do this by we transform the correlation graph to a two-hop graph, where the edges here, in this case, are given by the dashed edges here. And then we compare the correlations to the shared neighbors for those two-hop edges. And we can weight those edges with this similarity measure. So in this way, we can transform the correlation graph to a similarity graph, where again the objects are given by the vertices are given by the objects, and the weights of the edges are given by the similarities. And this can be implemented with just a few lines of code. We have implemented this in Spark, but it's only a handful of core transformations. So you could use some other system like Flink, for example, to implement this. So here are some examples of how these similarity networks can look like. So again, this is completely domain agnostic. So we have here similar words are linked together when looking at a corpus. We have similar artists that are linked together when looking at playlist data, using that for correlating artists. And we even have codons, similar codons in terms of which amino acids they code to in DNA, using from empirical estimated mutation frequencies. So this is very general. So I said before that we utilize this locality to make this fast. Another thing is that these correlation networks are typically very sparse. Most objects are not correlated. So, for example, if you have a large social network, you pick two persons at random, they most likely don't know each other. So it's really sparse. So locality and sparsity makes this scalable, and this enables us to do this for really large graphs. And also, I think this is the key technical contribution of this work. That is that we can calculate the similarities between all objects. It's not just so it's a scalable way to calculate the similarities between all objects for very large correlation graphs. So some more examples. So we have looked at done some experiments on Twitter users, and this is the similarity graph from that case. You could also look at hashtags. Again, this is similarity graph. Or relating similar words in Wikipedia, from Wikipedia. And in all these three cases, you can see that, I mean, there's clearly a structure to these graphs. They are not random. And this is another, benefit of this approach, that we can find these larger scale structures in data with respect to how different objects are correlated and how they are similar. So one thing here is that these are very grouped. I mean, these are clustered. So you can use your favorite community detection algorithm, for example, to find these clusters, and each cluster constitutes a concept. It's a group of objects that are intersimilar, objects that play a similar role in the data. So this is some examples from text, where you get US states, you get newspapers, colors, different types of vehicles, and so on. But a concept can also be an object. So we may have these higher order concepts. So one way to find these is to simply calculate the correlations of the objects, transform them to similarities, and then find the concepts from the similarities, and then recalculate the correlations in terms of these concepts, and then iterate this procedure to get concepts of concepts. So this is, for example, when applying this to playlist data, like this, you get these hierarchies of similar artists. That you have one high order concept, the topmost concept here, that consists of 3 branches of subconcepts that are each. And by the way, these are the ground truth theories. The labels here are from tags that user put on the artist. So you get these, subconcepts of subgenres like alternative rock, rock pop, and classic rock, and then these are in term form a higher order concept. And you could also, to go back to the other representations I showed in the beginning of the presentation, you can represent these hierarchies as circles within circles. So use this so-called circle packing. So these are words from Wikipedia again. And so then we can get these hierarchies of concepts. So here is one example where we have different directions or headings. North, south, west, east form one concept that in turn form higher concepts and so on. That in turn, these in turn together form a concept with left and right, I believe. Yeah. So what are the next steps? What do we want to do next? So far we mainly worked with developing this method and trying it out and evaluating it. So there is really not a shortage of possible applications here. So there are a lot of things that we would like to apply this on. And in several different domains. So we have been, one interesting area is in molecular biology and in medicine, how to relate biomarkers and symptoms, for example, or in to analyze protein interaction networks to find possible to guide further experiments to find possible interactions based on how of the similarities in the existing known interaction network. And also I showed some examples from Twitter, so it would be interesting to use this to analyze social media or social systems in general. And I didn't mention that, but we just started to look at that case, and you can see some really strong structures there. And in that case, it's one indication is that there are a lot of these very clear clusters in the user networks and in the tag networks are due to bots or subgraphs of bots in Twitter. So this could be one approach to really get rid of unwanted bots or unwanted spam, removing spam. And also in terms of method development, so far we mainly done this for batch processing. But we would like to do this in a streaming fashion to be able to build these similarity graphs incrementally from data. So if you're interested in the nitty-gritty of these, the method I presented, I encourage you to have a look at these papers. And they are co-authored by Daniel Gillblad and Theo Vasilodis here at SICS. And also, feel free to contact me if you have any questions or if you're interested in some collaboration or something. Thank you.
Right. So, questions. There is one question up there. Does similarity have to be described in shared surroundings?
Let's see. There are several possible ways to define a similarity, and we wanted to find the simplest one in terms of the correlations. This is the way we do it. Is to look at. If you interpret this as a vector representation and you compare vectors, this is the implementation of this. But we have also talked about using several hops in the graph to relate objects. So you can to get a similarity between objects that do not necessarily have a link in the similarity graph, but that you can go several steps. Yeah.
Right. And this is a very good question. Can you label the concepts automatically?
Not currently. We haven't really looked into that. But there are approaches for summarizing text or for labeling text automatically, and I think that we could use similar approaches for labeling the concepts. But that's a very good question. Yeah.
Great. So let's thank the speaker.